So let me share my screen. So today is to explain the big picture of the project, but the part that should be confidential is I will not make the record, but let me try to explain the general like the framework that you should know for your presentation and also your own like the project. So what we are doing is the quantum computing project in a specific way. And it looks a little bit weird in a way that the first, like the problem set was just a matrix algebra, as you saw. It's kind of tedious, kind of doable, but yes, it's just what it is. And all of a sudden for the problem set two, some strange geometry entered and some very like the alien languages also entered, and it's hard to see what the heck was going on here. So in order to explain, I need to explain the definition of the collection of the one qubit. So when we talk about the one qubit, then you should think of it as this as a replacement of bit. So what is the bit? So either it's just a zero or one, right? So there's just a voltage like a threshold. So we regard some of the like the stage as activated or otherwise it's just not activated. It's very simple. But the quantum computing is based on the axiomatic approach from quantum mechanics. So that in order to allow the probabilistic interpretation, we will just regard this as an element of so-called C2. So, so this notation looks quite like the fancy, but let me write this as a Z consists of Z1, comma Z2. And each like the Z1, Z2 are just nothing but numbers, complex numbers. But from the quantum mechanics point of view, so we want, so this is just the sort of the axiom. We want to provide probabilistic reinterpretation of so-called quantum states. So, so this is just the axiomatic part. So for our like the project, let's just simply just accept this as a part of the mathematical modeling, so that the one qubit, so that we will just require the norm of z equals one. And let me just recall from the first like the homework set. If you just look at the definition of the dot product, so z dot z, this just means that so z consists of z1, comma z2. And same z also consists of z1, comma z2. And if we take the now the product, that product, then this is a now Hermitian inner product. Then now you know what this is for sure. So that not this guy, what do we need to put? Complex conjugate. Agree? Complex conjugate. So that if you put same two vectors, then it becomes non-negative real. So that this becomes z no, 1 norm square plus z2 norm square. Agree? So without complex conjugate, we cannot say so. So we always make z dot product with z is non-negative for any like the z. So this is always greater than equal to zero for sure. Is that okay with you? And we'd like to make this guy as a definition of the z norm square. And we always make this equals one. So meaning that z dot z with the square root always equals one. So again, a collection of one qubits is naively identified as a collection of Z in C2 satisfying the norm equals 1 for a moment. Is that okay with you? So this is we take as a all possible like the collection of the one qubit. So now I want you to imagine, because our project is quite geometric. So I want you to really imagine video on like the intuitive like the interpretational way. So let's just imagine how it look like. So for example, let me start from like the C1. So C1 means just complex plane. Is that okay with you for your intuition? So C1 is same as R2. If you imagine the picture, are you with me up to here? And if you draw the picture, let me draw the picture here. Let's just draw the plane so that you can just assume x-axis correspond to the real part, y-axis correspond to the imaginary part. And the quantum mechanical point of view should make this condition for the probabilistic interpretation. So let's also just make our norm here equals 1. What does that mean in the picture? So it just means the unit circle. Do you agree? Unit circle. So if you just make R like the Z, whose like the magnitude equals 1, then it will be the unit circle in either C1 or R2. Is that clear? So do you know how to really mathematically write down each of the element of the unit circle? How do we write it? I am asking you that you already saw it. So if you parameterize the angle starting from x-axis, rotate counterclockwise. So then what is this element?
Cosine of theta plus I sine theta.
Perfect. Yeah, polar coordinate. And this can be also written as a so-called Euler formula that e to the I theta. Is that okay with you? So let me just write down Euler formula. So this is very important identity that I highly recommend you to keep even after you graduate from college. So e to the I theta equals cosine theta plus I sine theta. So in particular, if you plug in, say, pi, then it will give you cosine pi plus I sine pi. So what we know is sine pi is 0 and cosine pi is -1. So it gives you the number of -1. So this is a magical identity in a way that historically negative number, like the Euler number E, imaginary number I, and number pi are all sort of the mysterious numbers in history. They are all related by using this Euler formula. And this is coming from e to the I theta equals cosine theta plus I sine theta. And the way to drive this identity is from calculus. So let's just accept this as a fact. Is it okay with you? So we will use this fact for our like the necessary derivation for today. So I want you to click this intuition. So I will give you the time if that's helpful. So let me be clear. So if you just parameterize this like the unit circle. So unit circle as a set consists of e to the I theta, and theta is any real valued. Is that okay with you, intuitively speaking? So because the reason I am explaining this for you is you should click the visualize intuition of the collection of the one qubit. So in order to do it, let me start from the simplest like the possible case. Eventually, this is directly related to understand the collection of one qubit as a Bloch sphere. But anyhow, so is this okay with you up to here? So this is the first imagination. So if you need time or if you have any like the questions, let me know. This is A. So B, let's just increase one dimension higher. So now I'd like to just look at R3, R3. Then you can draw the picture like this, right? So it was previously XY plane. Now it is X, Y, Z, three axis. So still let us just collect all like the unit vectors. Then if you try to draw it, we'll get this. Does that make sense to you? I mean, just the surface. Then now this the object kind of you are now kind of getting a little bit angry about it. But yeah, anyhow. So this is we can write this as a so-called a two-dimensional sphere. So let me clarify two sphere. because this is two-dimensional. We are not talking about the interior, we are talking about just the boundary. Is that okay with you? Two-dimensional like the sphere. So now let's move on to our like the original like the case. So let's just look at this case again. This case again. So if I just zoom in, this is R4 because C1 correspond to R2. Is that okay with you? C1 correspond to R2 so that C2 correspond to there should be four independent tuples. So it is now R4 and the one qubits are the collection of the still unit vectors. So now it's hard to really imagine because now this is beyond our like the way to really concretely visualize. So I want you to think this as a three steps. Step one, in R2, unit circle. In R3, sphere. In R4 or C2, three-dimensional sphere. So that now I want you to at least mathematically click, this can be written as a S3 because this is a sphere of dimension 3. Let me just repeat three steps. In R2, unit vectors, circle. In R3, unit vectors, two-dimensional sphere, do you agree? So that's why we denoted them as a S1 and S2. And we'd like to go one step higher to describe the qubit. Now we have a C2. You cannot really draw it, but this mathematically, this is sort of a nonsense, but still we can talk about it. So the collection of the unit vectors in C2 should be the three-dimensional sphere. Does that make sense to you? Any questions? So this is the first like the necessary observation you should actually make. And there's a one necessary another concept that I should explain. So that's the concept of the group. So you might saw this concept before in like the either the high school or the even middle school, even though you didn't use this like a term. So we will make everything very like a concrete. So let's just look at the unit circle again. So this is a set concept of e to the I theta, and theta is any real valued. Is okay with you? So the reason we call it by this the group is that so it this guy is closed under multiplication. So this means that if you multiply by any elements on the unit like the circle, then from the exponential law, so this is kind of okay with you, right? So that if you have a unit circle, so if you have the angle parameterized by theta, angle parameterized by phi, then you should get kind of rotate by theta plus phi like this. So that it is close under the multiplication first. And you can also see that it omits the identity element. So these are the materials that you will present in front of your friends in July. So that's why I explained this to you. So this means that if you multiply by e to the I0, what is e to the I0? E to the 0 equals what? What is e to the 0? 1. Multiply by 1 yields nothing. It should be the same. So that it has the identity element, meaning that if you multiply by the identity element, and we say the identity element because such an element uniquely exists, so that it will not change anything for any theta. Is that okay with you? It is kind of just looks trivial, but actually it is not trivial. So it also admits the inverse element of each e to the I theta, meaning that i.e. So if you multiply by, it looks also quite tedious. If you multiply by e to the negative I theta on e to the I theta, what do you get? it should be e to the 0. So it should be the identity element. So that we can always recover the identity element. Is that okay with you? And it also satisfies there are four selector rules, so-called the associative law, meaning that if you multiply by e to the I theta 1 times e to the I theta 2 first, and then multiply by e to the I theta 3, so in this like the order, then this equals e to the I theta 1 times e to the I theta 2 times e to the I theta 3 with the order described from this parenthesis, right? So this is a so-called the associative law, that meaning that we do not care about the computational order. So if it satisfies those four rules, we call such a like the set the group. That's the definition of the group from abstract algebra. And for the like the CS like the direction, so the most like the useful like the mathematical like the subject is like this one, abstract algebra. And anyhow, so we will only look at just a unit circle for the example. Is it okay with you? So that you can just assume. So S1 is just has a autonomous group structure. Just that's it. Then actually two more fancy concepts for today. So now I need to explain the concept of group action. So in general, so such a concept is usually studied for the math major in their like the at least second year or the third year of the major study. But for our like the project, so you just look at this example. So it's a little bit like the heavy, but still. So what we usually do is we take this weird notation, and this is the major part of today's like the conversation. So this like the notation means the following. So S1 is e to the I theta, right? So any element of S1, just a circle is e to the I theta, and it's like the element of Z is written as a Z. So let me write as just a Z. So the Z consists of Z1, Z2, Z1, Z2, and this satisfies the norm equals 1. That's the meaning of the S3. Is that okay with you? S3. So we can take the square, still norm square equals 1. So this means Z dot Z. All right. So that we will kind of multiply e to the I theta on Z. Can you multiply it? So i.e., I'm just saying I'd like to multiply e to the I theta on Z1, Z2. How can you define this multiplication in a natural way? What's the way? So now you have a one complex value, e to the I theta. Then you have another like the two complex values, Z1 and Z2. And what can we do?
Do you do something with like the complex conjugate or something?
It's eventually related to complex
Oh,
conjugate, but you're thinking more heavily.
magnitude.
Sorry?
Do you like divide by the magnitude
It's more
or like
here. So just a
divide?
thing, you're like the easiest possible, like the version of the multiplication. So how can you multiply e to the I theta on Z1 and Z2?
Like distribute
Just
it.
distribute.
Oh,
Okay, it's just let's just think most like a tedious like a version. So we will define, so this is a notation to define e to the I theta Z1, comma, e to the I theta Z2. Then each component are complex vector values. Is that okay with you? Complex vector values. So you can actually realize the following like the magic. So if I just write down this like the further, then we already explained, we know this. You agree? This equals 1. Got it? Let's just write this part out as well. So let's just rewrite this as Z1 prime with Z2 prime. Z1 prime means e to the I theta times Z1. Z2 prime means e to the I theta times Z2. Let's just check Z1 prime bar plus Z2 prime bar equals 1. Let's check this. So why? So if you just plug in, then z1 prime means e to the I theta times z1, right? If you take the complex conjugate here, what is this?
E to the negative
E
I.
to the negative I theta, right? This is sort of nature, times z1 bar. Does that make sense to you? Complex conjugate on e to the I theta, you need to change the sign of the exponent. And z1, the complex conjugate is clearly just z1 bar. And just to repeat, e to the I theta, z2 times e to the negative I theta times z2 bar. You agree? Then now you can see that because all these are multiplication of the complex numbers, these two will be canceled. Can you get that? E to the I theta times e to the negative I theta. So if you multiply these two, because e to the negative I theta, so it just becomes e to the zero identity, just one, so it does nothing. Same reasoning. So this part will be gone, so that you can see that this now becomes z1 bar plus z2 bar. What is it? This equals, we assume, just one. So therefore, what you can see is that, so if you take this, so we will call it by the action on S3, you will get S3. Still, it remains on the same three-dimensional like the sphere. So this is what I today need to rigorously just explain. You might just still feel why I need to care about this. But yeah, this is necessarily like the ingredients today I need to explain. Is that okay with you so far? Any
Yeah.
questions?
No.
So now you are indeed ready to learn quantum like the computing project. So let me just repeat. So this is what you need to keep for today from now on in a way that, let me just repeat. So can you naively imagine the three-dimensional sphere? So this is the collection of the one qubit. Is that okay with you? Then what we did here is that if you put e to the I theta, then still it is the element of the S3. Is that okay with you? So now let me show you one picture that you saw this long time ago with me, but now you can kind of appreciate this like the picture in your own way. Let's look at this together. So do you remember this?
Yes.
Yep. So now I want you to imagine. So keep in your mind that we start from the S3, then we multiply by e to the I theta. Then if you think about it, so if you like the move theta from 0 to 2 pi, what happened? Circle. Then if you, so you should imagine this is, of course, we cannot really visualize three-dimensional sphere for sure, but you can kind of assume this is a three-dimensional sphere. Is it okay with you? Three-dimensional sphere is here. Then for each point on the S3, if you multiply by e to the I theta, then if you change the theta value from 0 to 2 pi, what happens? For each point on S3, we have the gray circle for each point. So that if you consider all possible like the collection, so the S3 look like something like indeed like this. It's kind of crazy picture, but I want you to now appreciate in your own way. So such a like the effect of like the circle. This is actually a great circle that for each point of z in a S3, we rotate by using e to the I theta. So this is called by the Glover phase that creates the circle on S3 for each point. Can you kind of get that? So that the inside of the three-dimensional sphere S3 has such a like the structure that each point you can multiply by e to the I theta that creates the circle in that orbit containing that point for each point of the three-dimensional sphere. Now this is a little bit geometrically heavy to imagine, but kind of makes sense, hopefully. Are you with me? So
Yeah.
now let me just go back to my iPad, like the screen. So this like the somehow simple like the expression of the e to the I theta group action with z gives you the effect of the circles for the orbit. Is that okay with you?
Yes.
I'm asking, is this geometrically click with your own intuition? Can you explain this in front of other in your presentation? This is what exactly you should explain. Yeah, so that you two need to really like the thing, and for our next meeting, you guys can ask me any like the detail and any like the point. So far, I actually tell a little bit lie that so collection of the one qubit is actually not S3. So this is I told you a lie. Now let me give it a real definition. So the definition of the collection of one qubit is the following fancy like the set. So it is this guy is the collection of the gray circle. Notation is very, very fancy. So this means, so what I'm saying here is that, so let me try to explain what this means. So this is the collection of the gray circle. And the gray circle itself is, as you saw, is a set. Is that okay with you? Gray circle, meaning that for each point, by using that group action, we can always like rotate one time. This is, we call it by the gray circle. And the one qubit, the collection, is not the element of S3, but each of the gray circle itself is the element of the one qubit. That's actually real definition. So let me now give you the picture again. So if you really look at this guy, this picture, so you can just assume this is the picture of the three-dimensional sphere. And we are not just thinking each point as a one qubit, you are really thinking one qubit as a one circle. This corresponds to one qubit, meaning that as long as they can recover from one to the other by just rotating gray circle, we just regard them as the same. This is also related to the quantum mechanics point of view of the preserving the level set or whatsoever. But the definition is now quite like abstract that this is a set of the set. And this set is the gray circle for the element. Is that okay with you? This is today's most like the heavy like the concept that for like the rest of the weeks you need to digest in the intuitive way. Any questions? So this is the definition of the real definition of the collection of the one qubit. So let me just repeat. What is the one qubit? One qubit corresponds to one cycle. And we collect all those one cycle. So that's the real definition. Then it's not over yet. Can you imagine how it look like?
Like the picture in front of us. No, I don't know.
You actually, so that was the point of the problem set too. So this is sort of the very surprising. This becomes two-dimensional sphere. So that we can really draw the each one qubit in R3. This is called the Bloch sphere. So let me just repeat. The mathematical rigorous definition of the collection of the one qubit is not the point of S3, but the gray circle inside. So let me say in S3. So let me write down this clearly here in S3. And this is can be geometrically identified as a, this is kind of the very non-abstract, right? This becomes two-dimensional sphere. So this is the reason why they're each like the one qubit. Now let me use the familiar notation with you too for your own like the practice. So that we'd like to write down this consists of the first like the a cat like the vector, second like the cat vector, and then we wanna just put, let me just show the expression. Hang on. So let me just show you the expression with you two first, and then just write down this for you. So if you just search the Bloch sphere, so now you have a two-dimensional sphere. This is indeed a two-dimensional sphere, and each of the element is written, I mean, each of the one qubit is written like this. Let me just copy this expression on the iPad, like the note, and let me explain how to think of, so that you can now see it is written as cosine of theta over 2 and sine of theta over 2. I usually do not try to memorize this expression. This is not completely not necessary. You just need to search and just look at it. This is the expression of the each of the one qubit. And how can you really just think of? So this just means that you have a each point, then it has a two like the phase information, this angle denoted by theta, this angle denoted by phi. In the calculus class, this is called the spherical coordinate. So in summary, it's very simple. So what is the collection of one qubit? Just a two-dimensional sphere. Two-dimensional sphere. So each like the point of the one as a one qubit, so that you just need to look at each of the phase from the North Pole and also the trajectory along the equator. That determines each of the point. This point, you now see that should be determined by theta and phi. That would be that determines unique like the one qubit. So the collection of the one qubit, in summary, is just nothing but a two-dimensional sphere coming from this group action. In a way that we just consider the great circle in S3, and by using geometry, can be identified as a two-dimensional sphere that we will call it by the Bloch sphere. Then why we care. So now let's just go back to the problem set 2. And after just a few more words, I will stop to record and explain about the project. So now you know at least problem set 2 is related to understand the geometric structure of the two-dimensional sphere and the torus. Can you get that? Now you know the reality, how complicated that computation should be in real. But that was the like the necessary like the ingredient in a way to understand the geometry of the one collection of the one qubits. So I now need to explain just a one thing for the record, but before going further, I just need to provide you one necessary like the necessary definition. But let me know if you have guys any questions or any like the comments. If not, I will continue. So the notation for a standard notation. Even now you know what this is, right? From the problem set 2, you know what this is. Do you agree? This is not the notation for the quantum computing. So this is usually denoted by CP1. And I usually prefer to denote this by this guy. And this is usually called by the complex projective line. So for the record, I just want to give you the definition of the CP1. You know the definition of the S2 in a way that this is a collection of the three tuple that makes x squared plus y squared plus z squared equal 1. This is clear. But the definition of the CP1, even though they are exactly the same, they are the same, but definition itself is different. So for the record, I just will give you the definition here. That was the point why I need to explain the concept of group action. Is it okay with you? So now it is non-trivial. So definition. Complex project for one. This is heavy. And just keep this in your mind that Bloch sphere, what was the real definition? Collection of the gray circles. In S3, is okay with you? And this gray circle means we collect all possible like the e to the I theta times z. So that's the and we change its theta. It's a free variable. So each like a gray circle itself. This guy is a set. Is that okay with you? This is the Bloch sphere. Mathematically speaking, is a collection of a set, and we can just identify as just a two-dimensional sphere because we are considering set of a set. It's kind of mathematical nonsense. So it's hard to really visualize why that happens. So that's the point of the Hopf vibration eventually. It's okay. This is mathematically correct. All right. So now the definition is following. So consider the following. So let Z consist of Z1, Z2 in S3. Is okay with you? In S3. So what you do is we will identify Z consists of Z1, Z2, and Z prime consists of Z1 prime, Z2 prime in S3 if Z equals e to the I theta group action with Z prime for some theta, i.e. if Z consists of Z1, Z2, that is written as e to the I theta times Z1 prime with Z2 prime, or you can write this as e to the I theta Z1 prime, e to the I theta Z2 prime. Then we regard them as the same. Same for some theta. Same element. Is that okay with you? Same element. And we denote it by bracket of Z. Now you can initiate the problem set 3. So what is the definition of the CP3? Sorry, CP1. So this guy is defined as a collection of these guys. Z is any element of the S3. So here, this like the notation just means we collect all possible e to the I theta times the Z prime. Or theta, any like this here. So this is the definition. It looks a little bit abstract and messy. So that I highly recommend you not just a two but four to discuss about this definition to really click what is it. Is it okay with you? And next time we can discuss for detail about this like the concept and the intuition about this like the definition and how we can really visualize it as the same as a two-dimensional sphere and so on. Those intuition would be matter for you. So please try to actively discuss about it. And you guys can also request with for the meeting in the casual way. So if you wanna like the make some conversation. So this is the like the end of the like the record I'd like to make. So let me stop the record.